Welcome to the Business Calculus series, Integration by Substitution. Before we define integration by substitution, we need to review a little bit from derivatives. And in particular, we need to review the chain rule. The chain rule is used to differentiate more complex expressions than our basic functions. And the way we build up more complex expressions, of course, is we compose the basic functions, right? We have a basic function f and a basic function x, which are both differentiable functions, and instead of we plug the independent variable t into x of t, and then when we get the answer, we plug that answer into f. And so we obtain from this a much more complicated behavior for our function. But we can still compute the derivative. And the way we computed the derivative was that, as you see, the derivative with respect to t of f of x of t is f prime times x prime. If we write the last line in Leibniz notation, then it's easy to see that df dt is equal to df dx times dx dt. What we want to do is use this to find antiderivatives of compositions of functions. The anti-chain rule, then, would be a way of finding the antiderivative of an expression involving the composition of two functions. However, we can only do that when the expression contains the product from the chain rule, both f prime of x and x prime of t dt, as shown in the slide. Now, there are some general formulas for how to do this using our basic expressions. But I think examples will help us understand what it is that we're doing, and then we can look at the equations. All right, in our first example, we're integrating a more complicated expression here, 3x plus 4 to the 10th times 3 times dx. And what we generally do is we identify a function, an expression, and pretend for a moment that we can't see its more complicated details. If u is 3x plus 4, we can certainly compute du dx. It's just 3. But we don't write it this way. We write it in differential form. Du equals 3 times dx. And we do this for a reason. Because we've identified u to the 10th, but notice in differential form we have also identified du. And so what we realize is that we have the integral of u to the 10th du. And this is a basic expression, so it's easy for us to compute the integral. After all, it's just u to the 11th over 11, right? We use the power rule, plus c. However, it wasn't u that we originally wanted to integrate. It was the expression 3x plus 4 to the 10th power. So we need to replace u with its definition. We complete the exercise by replacing u with 3x plus 4 to the 11th power divided by 11 plus c. And we have found an admittedly more complex antiderivative to a more complex integrand. Let's look at another example. What is the antiderivative, or the integral, of 4x squared times the quantity square root of x cubed plus 5 dx? In this case, again, we want to identify the expression u. Here we have x cubed plus 5. So u is going to be x cubed plus 5. And we're going to write the derivative in differential form. Du equal 3x squared dx plus 0 dx, right? But we don't have a 3x squared dx here, right? This is the other part of our product. We have a 4 dx, and is there any way we can arrange for the right-hand side to be a 4x squared dx instead of a 3x squared dx? Well, sure. We can multiply both sides on the left and right, both sides by 4/3. And we get 4/3 du is going to be 4/3 times 3x squared dx. Now we're in a position to write our integral. It's the integral of u, square root of u, du times 4/3. Okay, we can simplify this a bit. We can factor out our 4/3, and we can write u using a rational exponent. And now we have something we can simply apply the power rule to. So we have 4/3, and we add 1 to 1/2. 1/2 plus 1 is 3/2, so we have u to the 3/2 divided by 3/2 plus c. Well, we've got some algebra to do. To divide by 3/2, we're going to have to invert and multiply. So we have 4/3 times 2/3 u to the 3/2 plus c. So what does that give us? 8/9 u to the 3/2 plus c. And now we have our result. We have our indefinite integral, our family of antiderivatives. Let us continue in this type of an example. So we look hard at our expression. We see a complicated expression, but we also see beneath the surface that this is 1 over a simple expression. All right? So we identify u as 4x plus 7. We write the derivative in exponential form. Du is equal to 4 plus 0 dx. However, we have a 1 dx, not a 4 dx, so we'll divide both sides by 4. Now we're in a position to write our integral as 1 over u, and we'll replace dx with 1/4 du. We'll factor out the 1/4, and we'll have the integral of 1 over u du. We know how to integrate this. We obtain 1/4 of the natural log of the absolute value of u plus c. That's 1/4 of the natural log of the absolute value of 4x plus 7. Let's write that a little bit clearer. Plus c. Just 2 more. We want to do a couple examples involving the exponential functions. We identify u here. Now, u is going to be this expression in the exponential function, right? U is going to be t squared. So in differential form, du is going to be 2 times t dt. So we can rewrite our integral. We can replace e to the t squared with e to the u. And we can replace our 2 t dt with du. We know how to integrate e to the u. du, it's e to the u plus c. And so now we're ready to replace u with its original definition, and we get e to the t squared plus c. Just one more. For the last example, we want to identify the expression in the exponential function. This is minus t squared. So we'll set u to be minus t squared. Now we will differentiate implicitly and obtain the differential du equal minus 2t dt. However, we have a t dt, not a minus 2t dt, so we'll have to divide both sides by a minus 2 and get minus 1/2 du equals t dt. Now we're ready to rewrite the integral as simply e to the u. We'll replace our t dt with minus 1/2 du. We can factor out the minus 1/2, and we now have the integral of a basic function, which we know how to compute. The antiderivative e to the u du is just e to the u, so we get a minus 1/2 e to the u plus c. And now to finish, we just replace u with its definition. We have minus 1/2 e to the minus t squared plus c. To integrate, in general, u to the n, u prime dx, then we get u to the n plus 1 over n plus 1 plus c. We can integrate e to the u, u prime dx. We can integrate 1 over u, u prime dx. Notice in each case you're seeing the chain rule in reverse. The idea is to identify the u, the expression that will simplify your integrand into a basic function, and then use whatever constants you need to arrange for the differential that you have in your integrand to match the differential that you have in your substitution. Now let's see if you can obtain an antiderivative on your own. Please integrate 3t squared times the quantity t cubed plus 4, all raised to the minus 2 power. So the only thing raised to minus 2 power is the quantity t cubed plus 4 times dt. You may need a piece of paper and a pencil. Let me give you some choices here. Is it the first or second, the third, the fourth, or none of these? Thank you.